Um, okay, so it's a pleasure to introduce Maria Monguió today as our lunch speaker. And I wanted to thank her for being willing to do this at what is a pretty late time where she is. So Maria is at the University of Barcelona and works on a variety of topics, trying to understand the structure of the Milky Way, in particular its spiral arms. And she's going to tell us today about characterizing the Milky Way with Gaia, IGAPS, and Weave. So over to you, Maria.
Yeah, thank you, Andrew. And thank you for providing me this opportunity to talk to you today. What I'm going to talk about today, this talk is going to be rather eclectic in the sense that I'm going to mix slightly different topics, slightly different projects that I'm involved with, and also the science we're doing with each of them. Feel free to stop me if at some point you think something is not clear or so on. So basically, I mean, main topic of my research is the Milky Way. Obviously, that from our perspective is just a band, a bright-ish band in the sky. And then I guess the main question is, why do we want to study the Milky Way in the first place? I mean, obviously, it's because, okay, it's our galaxy, it's our backyard, so we want to see what's around us. But also because, I mean, it's the closest galaxy we have. Okay, if we look at other galaxies, well, we have I mean, our galaxy is obviously a bit more difficult to study than others because the forest can the trees can let us see the forest, and if we look at other galaxies, we can have a clearer view of how they are, the main shapes, and so on. And it's a bit more difficult to do that in our galaxy. But at the same time, it's the galaxy that we can study in more detail, and we can study in more detail positions and movements of stars that we cannot do in other galaxies. So it is really a key piece when we want to study galaxy evolution in general, because we can really study in much more detail than other galaxies. And if we talk about galactic astronomy nowadays, obviously we have to go through Gaia. Gaia is this ESA mission that so far has been revolutionizing galactic astronomy already with the different data releases that has provided, and more than will come. Gaia has been scanning the sky since 2013 that was launched, and basically it has been measuring positions of stars and all the objects that cross the focal plane of the instrument since 2013. And the latest release that we've got is this data release 3 that came in 2 different batches. In December 2020, we already had this early data release, which provided positions, astrometry, and brightness, basically provided G magnitude for 1,800 million objects, 5 parameter astrometry, meaning positions, proper motions, and parallax for 1,500 million objects, and for the same number of objects, color photometry, basically PP, RP, or what we call blue photometer and red photometer. There was a second batch of data, much more innovative data in that case. Last June, there was a release that included much more information in different shapes and sizes. We got actual spectra. So these blue and red photometers are actually not really a photometer, but it's like a very low resolution spectra. And all these spectra, well, not all of them, but around 200 million of these spectra were provided in this data release. There were also object classification and physical parameters for around 500 million stars, the ones better behaved. And also the radial velocities, in that case for the brightest ones, and for 33 million of them. These radial velocities come from this radial velocity spectrograph that basically what it provides is a higher resolution spectra around the calcium triplet. This resolution is around 11,000. So, and actually these spectra are also provided now for around 1 million sources. There are also information about, for example, variable stars, 10 million of them, and there's also information about solar system objects. So Gaia observes or sees everything that goes through the focal plane, so also objects in our own solar system. And also there's an interesting list of quasars, if you're interested in them. Obviously, there's a lot of new information going on here, and I think it's gonna take years to digest all this. And well, more will come. So we will have a data release for probably around 2024 or so, late 2024, if I'm correct. So I just wanted to show you a couple of images just to show you what Gaia is capable of. These are just some outreach images, but they help to give an idea of how great this instrument is and this data releases. So here at the top left, what we have is a view of our, like in the galactic coordinates. Basically, you have the galactic plane here, this is the galactic center, and the anti-center would be somewhere around here. And in that case, color is showing radial velocities for around these 30 million objects. And you can see them here, the Magellanic clouds that are moving away from us. And also these four bands, what basically shows is the rotation of the galaxy. So this is the inner part of it. Let me show you here. So basically this is the sun, this is the galactic center in this direction. So rotation of the galaxy goes circular. Can you see my cursor here? Can you confirm? Because
Yes, I can. Yeah.
Yeah, great. So basically, in this quadrant here, stars mostly move towards us, which would be this blue patch here. In this inner part of the galaxy, the stars would go the other way around, and the external part of the galaxy here that basically goes like away and closer to us. And that's basically what it's indicated in this plot here. In this bottom left one, it's basically the colors indicate the same, these radial velocities, but here you also have, in the shapes of these lines, you have proper motions. And in that case, proper motions here. So because proper motions are much larger for nearby objects, this is basically showing the proper motions with respect to the sun of the nearby stars. And this is basically weighted, this kind of dipole here. What it shows is the solar motion, actually, because these proper motions are not solar motion corrected. But there's much more here. They also provide an interstellar dust map where you clearly see the Milky Way with higher extinction here, the disk of the Milky Way with higher extinction. There's actually different kind of extinctions that are provided by Gaia. One of them is just provided by computing distances from parallaxes and absolute magnitudes from physical parameters and so on. And from that, you can get an extinction. But there are also some extinction maps and some extinctions coming from deep interstellar bands directly from the spectra. So there's a lot of things going on and lot of information provided. And also they provide chemistry. And here you can see that in the disk where you have more extinction. So basically you have here like more nearby stars and disk stars that are more metal rich. This blue patch here is basically the bulge where you have more metal poor stars. As you go out of the plane, you can start seeing like more stars farther away, and they might have slightly lower metallicity than nearby in the disk, and also in the halo you have kind of a mix of disk stars and then going to the halo. So yeah, there's really a lot of information, and it's really being mind-changing all this information, and there are lots of studies already showing things that we didn't know about our Milky Way, and Gaia is really changing everything in that regards. But as usual, astronomers, we always have more, and we always manage to find what's missing in the data and what extra data we need to go ahead with our studies. And just to mention some of these points here, one of the things that we might want to have extra from Gaia is like photometry in different bands. Photometry is provided by Gaia is basically indivisible, but there are some regions in the blue part that are not really well covered. Obviously, if you go also in the infrared or ultraviolet, of course. Radial velocities, since these are basically taken in the calcium triplet in the red region, it's not very good for blue objects, and also it only goes up to magnitude 17 or so. So there is a lot of lack of radial velocities for fainter objects. So this is really a gap for improvement here as well. You can have obviously spectra in wider ranges or in higher resolutions, to get abundances, for example. So the way of getting all this information is going to be, at least for now, through on-ground surveys. And I'm going to talk especially about a couple of them today here. And these are for example, IGAPS and WIF that I wanted to talk to you about. IGAPS is this INT galactic plane survey that is covering the northern galactic plane. and WIF, which is this multi-fiber spectrograph that is being commissioned at the William Herschel telescope. I'll get into that in a moment. So let me start with IGAPS. IGAPS is this photometric survey, which actually it comes from, historically, it comes from two different surveys, IFAS and UVEX. And basically, one of them was covering I, H alpha, and R, and the other one R, G, and U. So we kind of merged the two of them in the sense that these three bands always are going to be observed together. And that helps a lot with calibrations afterwards. And then R, G, and U are also observed always together in the sense that you always have two measurements for R at different epochs. So as I said, it covers the northern galactic plane at latitudes plus minus 5. We recomputed all the astrometry and we linked it to Gaia DR2, which is what we had at the moment. And the photometric calibration is linked to pan-stars, especially for G, R, and I. It's all been recalibrated through pan-stars. For H alpha, it is actually linked to the R band with some tricks with it there. And then we also have the U band. I should mention that the U band is not completely uniformly calibrated. So if you want to use the U band, you have to be a bit careful there. There is a basic calibration, but it's not uniformly calibrated. So just to give you an idea of basic characteristics of IGAPS, about depth and limiting magnitude around, well, this is mainly the distribution of the different fields and what's their limiting magnitudes. Around half of the fields have limiting magnitudes above 20 magnitudes for I and H alpha. For R's and U, the half of the fields reach around 21.5 magnitudes, and for G, you can go a bit deeper up to like 22, 22.5. The normal PSF, full hub maximum, which encloses standard seeing plus instrumental effects, usually it used to be around between 1 and 1.5 seconds. And when we talk about astrometric errors linked to Gaia DR2, the differences, the median differences in different fields between our astrometry and Gaia's is around 0.03, 0.04 seconds for most of the bands, with U always being a bit worse. U always provides a bit more problems than the other ones. And this plot is just to show you how things improve when we provide like different steps of the calibrations, and things usually go quite well below this 0.1 magnitude in error. When we talk about photometric errors, here you have a plot with the errors as a function of magnitude for the different bands. I, H alpha, Ri. Ri is the R, the IFAS part, and Ru is the R, the UVEX part. So these two are measurements that I was mentioning before. And here in black, you have like the nominal errors coming from Poisson noise of the measurements, which tend to go to 0 for bright magnitudes. But then in red, you have a slightly better idea of what the errors are actually, because those are computed by averaging or by checking the difference between two measurements of the same source. Basically, since we always do for each field, we observe them twice with a small shift in order to avoid CCD gaps and bad pixels or cosmic rays and so on. You at least always have two measurements of the stars, and then in the overlap regions and so on, you may have even more on that for the same source. So checking these differences between different measurements of the stars, then you get this kind of red trends here. And in that case, what you see is that for most of the bands, you always go below this 0.02 magnitude error between ranges of magnitude 13 and 19 or so. Obviously, for faint magnitudes, things go a bit upper, like worse magnitudes. And also, usually, you may have some problems in the bright end due to saturation effects. The sources, even saturated, they are there, and usually they are flagged. The catalog provides lots of different flags in order to indicate when something may have been wrong. And again, U is a bit worse than the rest, as mentioned earlier. Just here, roughly providing some numbers. The total catalog has almost 300 million lines, but not all sources have all bands. Actually, U, for example, is one of the most restrictive ones that are not, as you go to more distinguished sources, for example, that are redder. You may have the red bands, but not the U and so on. And when you compare with Gaia, I wanted to give it a feel of how deep IGAPS is when you compare with Gaia. And here we've done a cross match in two small regions, one at L60, the other one at L100 in this galactocentric different directions. This is a much more crowded region, and this is less crowded. So starting for this one, you can see here in cyan, these are the sources that are in IGAPS and not in Gaia. So basically that indicates that IGAPS can go deeper than Gaia in this region. And here in yellow, you have the sources that are in Gaia, but are not in IGAPS, because IGAPS may have missed them or because crowding, because actually if you go into these crowded regions, this yellow part is higher. We are missing more sources in IGAPS that actually are in Gaia, and that may be partially at least due to the fact that Gaia has more astrometric sensitivity, has more resolution in astrometry, that because of the pixel size, obviously. But apart from that, IGAPS goes slightly deeper usually than Gaia. I wanted to briefly mention as well the BFAS Plus survey. This is the twin in the south of IGAPS. This is the PST photometric H-alpha survey of the Southern Galactic Plane and Bulge. It covers basically the same southern plane ±5, with a slightly larger area here around the bulge, with some gaps because we ran out of manpower basically to keep observing all this. But apart from these white patches here, it basically covers all the Southern Galactic Plane with the same bands as for IGAPS, a slightly better resolution, and also quite deep in the same order of Gaia. You can see more and load the data in this web page here. This survey, it hasn't yet been homogeneously calibrated. Actually, there are currently some efforts going on in this direction, and we hope to have this published relatively soon. Okay, I presented IGAPS and BFAS, but actually I wanted to provide some of the typical examples of science or uses of this catalog that we've been developing so far. And one of them is, well, IGAPS is quite good at selecting different kind of sources. One of them is emission line stars. So basically, I'm here presenting you with this color magnitude diagram, which is R minus H alpha versus R minus I. This is a quite useful diagram. It will show up later again. And in this case, obviously, because of this H alpha here, when a source is emitting an H alpha, it's shifted upwards. And so if it's shifted upwards enough, it will stand out from the main trend of the other stars. And we've actually used this in order to provide a flag of when a source it's possibly an emission line star. And all these gray ones are considered emission line targets here. We've only did this check in the catalog, at least for stars up to magnitude 19.5, because otherwise for finder targets, errors might start coming in the way, and we don't want to provide this flag. So basically in the catalog, we have flagged more than 8,000 emission lines stars that are above this certain line at a 5 sigma level, and over 12,000 that are emission line stars between a 3 and 5 sigma level. There are also some other studies from Matteo Fratta and collaborators that uses this data a bit farther away, also in the sense of computing or detecting emission line objects. Apart from that, another thing we have done is check variability. Use the fact that we have two measurements of R at two different epochs to check for variability. And in that case, what we have done is to check that, or to provide a flag that considers a star is variable if there is a difference in magnitude between the two R's above 0.2 and at the 5 sigma level, considering the errors of the two measurements. And with that, we have provided a flag for 53,000 variable sources. And we have checked that actually a fair number of them are already known, either MIRAs or eclipsing binaries or known variable sources. What else have we done with IGAPS? Well, another very useful tool are the actual images. The actual images are also available, and you can check either this Robert Grimmel et al. Publication, and they are also in this web page here. So how have they been used? I mean, the most used one for us has been H-alpha images so far, and one of them is to provide very nice images of, in this case, is this Shan 147 in the supernova remnant in the anticenter, but also to detect planetary nebulae and extended objects. It has also been used for that. And the latest one that we have used is to detect, to select nebular targets, like emission line targets for spectroscopic survey, like directly pointing at nebular objects that are emitting in H-alpha. And you can see here an example of this code. All these red points here are like outputs of this code that provides potential targets for spectroscopic surveys within that case. I'll come to that later. So now I'm going to shift to a slightly different kind of objects that we have been selecting with either IGAPS or BIFAS. Most of my job has been with IGAPS, but BIFAS can basically do the same job for most of these. And basically here, what we do is to use this other color magnitude diagram, in that case, the U minus G versus G minus R. And in these diagrams, the main sequence of the stars would like follow this blue line here, with the red being the giants. And since extinction will shift targets in that direction of this dashed red line here, basically that means that this is basically the same diagram. This is the main sequence, and this is the extinction line. A target being here, you really don't know if it comes from a not too extinguished F or a K or a very extinguished A or whatever. But what you do know is that all the stars above these lines, more or less, it can only come from this very early type of object. So basically this O up to B3. So there is this work from Mike Mooresmith that has been like selecting all these O and early B stars here. In that case, he did that for a region in the Carina region in using BIFAS Plus, and actually adding 2 mass data to all this photometry from BIFAS. He was able to compute also effective temperature, distances, and also extinctions, apart from providing a very good selection of these objects. And this selection, these kind of objects are very good to trace stellar formation and to know where things are being formed. So getting here into a bit more of a science, what we did here is to go in this, as I mentioned before, this Carina region. So this is just a face-on plot of the Milky Way, being the galactic center here. Here is the sun, and this star that I'm just mentioning is in this direction here, in this Carina, just crossing the Carina arc here. So what we did here is compute or to find all these kind of OB targets around 2 clusters in that area, namely NGC 3603 and Westerlund 2. And what we find here is using Gaia proper motions. What we did is to look for objects that were not in the core of the cluster, but had proper motions coherent with coming from this center here. That mainly could have been ejections in the past from this center cores, and that provides a lot of interesting results related with where OB stars form. Do they all form in clusters, or they can just be forming alone in the medium, or how many of them could be like coming from ejections, or how can they be ejected from this very dense cores? And you can almost see here in this plot, for example, that the color here indicates the time of flight, how long away would they have been kicked up from the centers, and you can almost see like 2 different circles, or two different ejection times have happened here, maybe even 3 if you take this yellow one here. So there's a lot of things still to be be studied here, but there is a lot of interesting stuff going on with all these ejections here. And even for this one, you can see lots of ejections here, but there are these two really critical ones that were ejected. If they really come from this Western 2 cluster, the ejection velocities were really huge. And also following in the same direction in the Carina arm, we did a study much more like in a wider area. So basically, the two clusters I mentioned before, NGC 3603 and Westerlund 2 are, I think it's this square here and this square here, but now we are covering a much larger area in the Carina region. And what we did here is like to study the whole kinematic behavior of the region. In this top panel here, what you have is, well, in this this is galactic longitude, and indeed in here we just provide the distance distribution according to Gaia parallaxes, and this is basically to show how bad they work here. How, I mean, we really cannot work with these distances. Just to show one example, this dark line here, this is all supposed to come from this NG3603 cluster here. So all these objects, like the bright ones, most of them, should be actually in the same position, and Gaia distances locate them from between 5 and 9 kiloparsecs. So really the distance errors here are really important. But when we work with proper motions, those are really good, and we can really do a lot of stuff with them. This is just the proper motion in galactic latitude, so the vertical one going away from the plane. And this is more or less as we expected, so around 0. Actually, we don't expect them around 0 because this has been not solar, the motion of the sun has not been corrected here. This is just solar, like heliocentric mu b. So basically, since the sun is slightly moving upwards, we do expect this to be slightly below 0 as it's happening. And the striking one probably is this mu L distribution. The blue line in the 3 panels basically show where we would expect, according to circular rotation, the Carina arm to be. So the values are more or less around here, but what is really striking is this like kind of sawtooth pattern going on here. Apart from this this batch here, that is a known and more distant group of stars, the other ones is a bit striking to see this sawtooth or these different lines going on. And it's still not clear for us what is going on with them. We do expect them to be related maybe with the parent cloud that form those stars, or maybe due to the interactions with the Carina spiral arm. We did check that cannot come from the fact that we are seeing different distances. It's really not compatible with that. Also, because of the fact that we've seen that somewhere else. Actually, well, not we, but Quintana and Wright, some colleagues of us, did see similar patterns, and this is in Cygnus. And obviously in Cygnus, distances are much closer, and the distances are really good. So in Carina, we've also, in Cygnus, we have also seen this kind of sawtooth shape here. So more need to be studied here, and one of the things that we're really missing in all this area is radial velocities. Obviously, for OV stars, these very high extinguished OV stars, Gaia doesn't provide any good result, but we'll need something else in that case to get radial velocities. We do actually have a very few radial velocities. There is a study, Drew et al. From last year, that they got around 160 radial velocities, in that case around Westerlund 2. So it's in a very small area from the previous slide. And in that case, since we have now 6D for these objects, so we have the distance, we have the position, we have the proper motions and the parallaxes, we can shift into a galactocentric frame. And here the velocities that you can see here are galactocentric. So basically PZ is the vertical one, and that now, since it's galactocentric, has been corrected for the solar motion, and now we do get, as expected, something around 0, except from some outliers that have been identified. For the B5, which is the circular rotation around the galactic center, you get something around 240 to 30 to 40, which is coherent with the galactic rotation. And the striking one, or the surprising one, is that BR, which is the radial one with respect to the galactic center, and according to circular rotation, you would get something around 0. You get something that is clearly below that, around -10 kilometers per second. Like all stars in that region, like tend to go towards the galactic center. And well, this is still obviously it's a very small region, and it's difficult to know what's going on there. And again, we still need more radial velocities to complete the picture, but it's an interesting result so far. Okay, let me change objects here now. So now I'm gonna get into A stars. Do you see? I'm seeing these up here. I'm not sure if you see it as well, or you have problems to see the upper part. I can take this out. Well, let's continue. So another kind of interesting objects we can select with IGAPS is A-type stars. These are rather interesting objects because they are relatively young, especially compared with the type of objects that all people usually do galactic studies, which is more like FJK because they are more common, or even red clump giants and so on. These stars are usually much older. And since A stars are younger, they can trace like different kind of behavior, like more recent shapes going on, or interactions going on. And also because they are younger, they are also kinematically colder. They have less kinematical velocity dispersion, and that can help to trace features that you could not see otherwise. At the same time, they are like still old enough that they don't just trace stellar formation. They have enough time. They have had enough time to like feel the galactic potential or other potentials going on there. So they're rather interesting objects to study for galactic studies. And we can select them easily from IGAPS. Going back to this plot I showed before, this is this R-H alpha versus R-I I showed before that we use to select emission line objects. And in that case, here, the red line would be the main sequence with OB stars being here. A0, A2 would lie like down there, and then going up again with FJKs for the red, and the same for the giants in the blue. And in that case, extinction is shifting things to the right following this red line here. So basically, if we select targets down there, more or less here in this blue region here, we would be quite certain that we are actually selecting A0 to A5 or like early A-type stars that are useful for these studies. So for example, this is work done by Amy Harris, a previous PhD student of mine. And what she did is in two different regions now in the anti-center. So this is L178, basically the anti-center, and in this other direction also around 118. She had spectra, in that case for important few thousand stars in these two directions. This is ectospec spectra. And with that, she was able to compute using some MCMC codes. She wrote effective temperature, log G, V sin I, and RV by comparing the spectra with templates. And so that provided, if you add all the Gaia information, 6D information for these targets. And so she was able again to provide, to compute galactocentric velocities. And here you have the 3 velocities for the 2 directions. And for example, the U, which is the radial component as a function of galactocentric radius for these stars, there is clearly something going on these waves here that they are not really related probably to the spiral arms, because you would expect the Perseus arm to be here and the outer arm to be here. So the wavelength really wouldn't fit. And so that probably could be due to something else, namely some external perturbations, for example, going on here. When checking the rotation, here it's more or less as expected around, in that case, we see the value of 2020. Not completely flat, but not that different anyway. And this is the vertical one going away from the mid-galactic plane. And here there is also, again, like a lot of interesting shapes going on with this this part going up that could be related. I'll discuss that later with the warp probably of the galaxy. But when we go to the 118 direction, things look rather different. In that case, these wavy patterns are not so clear anymore. And in that case, the rotation curve looks to be going up instead of getting flat or even a bit down as it was doing in this other direction. And in that case, the vertical one looks a bit more flat. So, I mean, what that basically showed us is that things are not nice and tidy, and there are lots of interesting going on in different places that need to be looked in a much more extensive and coherent way. And that's where my current PhD student, Judith Ardèvol, she's now starting her PhD, is doing now. She basically is using a selection of A0, A5 stars, in that case, in the whole northern galactic plane. So basically, this is the whole IGAPS selection. Sorry, because I keep shifting the plots here. This is the sun would be here, and the galactocentric center, the galactic center would be in that direction here, which basically means that we are covering all this half of the galaxy here, more or less. And here what she's done is compute surface densities. This is actually density, and you see different blobs going on here and there that show different densities that maybe could eventually trace what would be spiral arms. This B shape here is Cygnus. And actually, you can also see a lot of radial features here. This may have two different origins. From one side, that could be distance errors, like parallax errors, although that's not that much the case here, because there's been a astrometric cut right here for good parallaxes. And the other one is basically extinction. So basically a huge cloud of extinction here in the Cygnus area would block the view of any stars going on in that direction here. This is basically the same plot with instead of plotting just surface density, this is kind of a local overdensity that helps to see structures farther away when here the actual absolute surface density is too low to see anything. So it like kind of helps to see better all these outer parts here. Hopefully Judith will be able to submit this paper soon, because she hasn't only looked at the actual densities, but obviously she went into the kinematics as well. And when we cross-match all these A-type stars in the north with Gaia and ask for also radial velocities, we end up only with 30,000 A stars. And the thing here is that we only get up to around 2 kiloparsecs from the sun. And still there is like different features interesting to be studied. This is galactic rotation, like B phi, in the sense of the galactic rotation. And there is clearly differences going on if you look at the anticenter or you look in different directions. We still have to recheck and to compare this with Amy's result from the previous slide. If you go for BR, like how stars move with respect, like into or getting away from the galactic center, and again there are some shapes here, but between the fact that here we are pretty close to our limits, observational limits, and that we don't go too far away with the radial velocities, it's a bit difficult to get strong conclusions. Let me just mention that as soon as we have BFAS homogeneously calibrated, we'll be able to like complete the whole area, also going to the southern plane. And this is the BZ, like the vertical motion. Difficult to see anything interesting here, except maybe for this red blob here of targets going downwards that I'll mention in a second again. Because what she's done also is go and check for all the stars that, even if they don't have radial velocities. And what she did here is check the vertical velocities with respect to the plane, but because she doesn't have radial velocities with all these stars, she just goes for the BB, which is basically the mu b, like the proper motion in the direction of the galactic latitude. but corrected to the appropriate distance to convert this into velocities. And that may provide some biases. This assumption does provide some biases, basically as you move away, basically from the anti-center. So you see this big red blob here of a star that looks that it's moving, they are moving downwards. And we've checked that that can partially be due to this bias, although we've seen here that it's not only that, there is something really going on, because if we do not have this bias, things are still moving downwards. But where we are pretty certain that we are seeing something real is here in the anti-center direction, because up to like 3 or 4 kiloparsecs from the sun, we start seeing that things shift into positive velocities. Basically, stars tend to go upwards from the galactic plane, and we've put that in this plot where basically color here shows the different directions. So things do not move much. This whitish part here, this is now in galactocentric, but up to more or less from 8 to 10 kiloparsecs from the galactic center, we start seeing that as we go farther away, the velocities, the vertical velocities keep increasing. And that's coherent with the model we have right now of the warp. Basically, we know that the warp is sort of upwards in this direction here, basically in this direction here. It's going south, it's south in this direction here. It's more or less, there's no warp in this direction here. So basically what happens is that the stars need to move from down here going upwards and then go up at the upper part of the warp and then going down again. So in this direction of the anticenter is where the maximum of the vertical velocity should be, as we are seeing here. So that looks as expected. Again, to complete the full picture and make sure about all of this, we still meet radial velocities, and I've said that for quite a few times now. So that's where width comes into place. So some of these radial velocities we are missing, we're hopefully going to be able to get them thanks to width. WIF is this multi-fiber spectrograph that is being commissioned in La Palma. This is the William Herschel telescope in La Palma in Canary Islands. This is the dome. This is the actual telescope. You can see the primary mirror. Now it's closed, covered down here. And here at the top end ring of the telescope, you have WIF placed. Or this is actually the plates and all the fibers and configuration goes up. The configure tools go up here. And then light will be transferred into this Nash-Schmidt platform here at the end. And this is one of the astonishing views of the plate of WIF with all the fibers located here. Just a few numbers about WIF. This is located, as I said, at the William Herschel telescope, which has 4.2 meters. The field of view of WIF is 2 degrees in diameter, so a pretty big one. And it has 3 different modes. It has the multi-object spectrograph mode, which can locate more than 900 fibers at the same time in each of the plates. It basically has 2 plates because the location of the fiber is rather slow. The robots go quite slow there, and it can take up to an hour of configuring one plate. So basically, while one is configuring, the other one is observing, and then they are tumbled, they are shifted, and the other one can start observing. So these over 900 fibers have a size of 1.3 arc seconds. And then there are the integral field unit modes that there is a mini, if you would call, there is a 20 budget examples of 11 per 12 arc seconds with a spark source of 1.3, like different. You can look at in the same 2 degrees field, 20 objects with compact bundles of fibers. And then you have the large IFU, which is a large compact bundle of 1.3 per 1.5 arc seconds. The spark source is a bit larger in that case. These are the 3 modes. And then when talking about resolution, you have 2 options. You have the low resolution mode, which covers the entire visible range at a resolution around 5,000. And then you also have the high resolution mode. Here the resolution is around 20,000, and you can actually cover 3 different bands. Actually, you can only cover 2 at the same time, the red one, and then you have to choose between the green or the blue to complete the observation in this high resolution. And I just wanted to show you this pretty cool video. Let's see if you can see it. Yeah, of the two robots. I hope you can see that one now. Yeah, so this is basically are the two robots. This is still in the lab, but grabbing fibers one by one and putting them in the focal plane. So basically that's what needs to happen, but not here down there at the top end ring of the telescope, which is pretty awesome. Let me get back to the slides. What's going on here? Yeah, sorry, I'll share it. There we go. Okay, just very quickly, some of the politics of the WIF instrument. This is a consortium of Spain, the Netherlands, UK, France, Italy, and these European countries. And basically 70% of the nights for the following 5 years are going to be devoted to the WIF surveys. And this surveys I'll mention in a second, that we've been preparing for quite a long time now. And the 30% remaining of the time of the nights will be devoted to the ING, the Isaac Newton group observations that basically will open through normal TAC time for ING countries, which Spain, UK, and the Netherlands. And they can be applied for WIF or other instruments, although I'm pretty sure that after they've seen how hard it is to place WIF up there, they will try to avoid moving it up and down as much as possible. And let me also mention that there is an international call for that. I think they're offered around 5% of the time, so it's not huge, but it's possible to apply for international time, and there's actually a call open now that ends at the February 29th. So if you are interested of applying for WIF, you still have a chance right now. And what about the timeline? So the first light of WIF was published last year in December 2022. I'll mention it in a second. And all things going well, LIFU in principle has been already commissioned, and they are now commissioning the MOS, the multi-object mode. And if things go well in March, we will start observations of science verification, and all the surveys will hopefully start in May, all things going well. So I just mentioned that there was some first light, and there was a first light release last December. And actually the observations of first light were LIFU observations of the two central galaxies. This is the LIFU packages of the two central galaxies of the Stefan Quintet. And actually this batch has 547 fibers, and actually with some shifts and dithering around this central position, they are able to produce spectra for around more than 31,000 locations in all this area. And both, that was observed in both high resolution and low resolution mode. And so they were able to provide radial velocities for this area here. And what they basically showed is that this galaxy here is coming quite quickly, at this 800 kilometers per second from the back of the other galaxy. It's like kind of a late intruder, they call it, to the group. And they also are able to provide spectra from different regions of this area, including in the center you have more old-ish stars, and at the outer part of the galaxy you have more star formation with its different spectral lines and so on, and gas going on in these other directions. Just let me mention that the red one here is a spectra in high resolution that they claim that we're able to get instrumental resolutions around 12 or 13 kilometers per second. We're hopefully going to get much more than that very soon. Just quickly mentioning the 8 surveys that are prepared for WIF. These include galactic and extragalactic options here. So basically, this galactic archaeology survey that basically complements Gaia with all the radial velocities that we've said that Gaia still lacks, mostly for faint targets, but also at high resolution in order to get metallicities and elemental abundances key for galactic archaeology studies, but mostly for all type of stars. So that's where this other survey, stellar, circumstellar, and interstellar physics comes in. This is the one I'm most involved in. And this one, the main targets are going to be these O, B, and A type stars, but also the different kind of other objects like red supergiants or YSOs, and also like interstellar medium targets obtained from this emission line object sorry, these emission line positions obtained from IGAPS images I mentioned before. There's also a survey of white dwarfs, and then several kind of extragalactic surveys. One is which is a LOFAR follow-up, another one which checks populations in external galaxies, galaxy clusters. There is also a survey with about quasars and so on. I mean, if you are interested in any of these, ask me or just ask one of the leaders of these groups. And I think, well, I did have a bit more detail about the SCIP survey I'm more involved with, but I think I prefer to stop, let it here. If you're interested in that, ask me, but I think I prefer to just leave some time for questions, if there's any.
Great, thank you, Maria. Very nice talk. And we do have time for questions if people have any. Andy, you put a question in the chat earlier. I don't know if it was already answered or not.
Yeah, it's not really germane to the main talk. I think the answer is its thickness. It doesn't matter.
Sorry, you see that the bulge is greatest metal pool. Well, yeah, basically, let me get back there because I had another. I didn't show this other plot I had here, but getting there. Sorry, yeah, this one. So basically, this plot goes a bit with this plot here, in the sense that this, what it shows is the average distance at each of the pixels, meaning that when you go outside the plane, you can get farther away. And so basically what you are seeing when you go here is basically the bulge. And in the bulge, we have usually more metal poor stars than in the disk, or like stars near us. That is what we have in this direction. Here you basically, I mean, this is distances, but still what you see here is actually a shape of extinction, right? So extinction makes that we can go farther away, and we are getting to closer distances, apart from the part of that you clearly see nice globular clusters here and there. So yeah, I mean, if I'm not mistaken, on this shape follows more or less the fact that that here you can really reach bulge where one would expect like lower metallicities.
Well, what
does that answer?
do you mean? What does that color, that blue color, really mean?
That basically means lower metallicities. So in red you have higher metallicity stars, or directions where higher metallicity stars dominate. While here you have lower metallicities. Basically, these are disk stars where you expect higher metallicities, and this is bulge stars. In bulge, you have some sort of concentration of stars that are linked to the halo, where you also have like low metallicities.
It could be the center of the halo, I suppose. But
yeah. I mean, somehow the bulge. Well, here we get. I mean, I'm not really an expert on this topic, but basically. When you talk about bulge and how this is formed, or if you have a bar, or what is the origin of the bulge, there is a lot of controversy about that. But it's sometimes it really like starts from the halo that it's like get stripped into the bulge, right? So in terms of metallicity, you have similar metallicity in the bulge that you can have in the halo in that sense.
Yeah, that's. I mean, there are lots of metal-rich stars in the bulge. That was like the history for decades, and okay, yeah, there is a vertical metallicity gradient. So maybe you're seeing that. Does this mean 1/10 of a dex, 3/10 of a dex?
I don't have the bar here. You should go and check the. Maybe I do have them here. I think I have the plot.
Yeah, it's not really pertinent to all the rest of what you really were talking about. No,
No, but I say that it can get interesting. I think I have the plot down here. Does it have the bar? Yeah, it is there. So basically, that you can go here at metallicities 0 to -0.3. So that's more or less the range here.
All right, any other questions?
Yeah. Well, if no one else has one, you had another figure where I think you were showing distances, and I think you were mentioning Carina, and there was a whole, not all the stars were at the same distance. And
Yeah.
I was wondering if you could explain that. Maybe I missed it.
Yes.
So is that just
Yeah.
due to binary motions, or why is that? Why was that?
You mean
Yeah, that one. Yeah, the top.
this one here, the top one. Yeah. So basically, what we're seeing here is stars in that direction here. So, but you also have some width, obviously, because I just put a line here, but actually there should be like whole range, like a triangle, angle here. And basically, when you observe from, let's say, this white line to this one, the red one here, what you are covering is different parts of the Carina region. You have like the near arm here that we can try to, we really kind of try to avoid the closer part of the arm. Can you see that one here? So basically, as you move to the tangent, you have the tangent here, and then the arm keeps going away in that direction. So basically, this point here in blue would be the tangent, more or less here. And then if you move to higher galactic latitudes in that direction, you keep following the arm going farther away.
So it's really just the arm, right? The rotation.
Yeah. Yeah. So this is just distances. So what you would expect, the arm, the perfect arm, like I don't really recall what model what we're using for the arm, but basically what we would expect the stars in the arm to be exactly in this blue line. Okay. And since O stars, I mean, you can obviously have O stars everywhere, but the star formation will probably happen close to the arm. We would expect most of the stars to follow like this trend, this direction here. That's why you have more stars here, which would be like closer to the tangent, this point here, and these stars a bit farther away, because you would like already be starting seeing this like the other side, the far Carina arm here. Does that make sense?
Yeah, thank you very much. And one more related one is, how far away, what's your star formation rate measurement distance limit? I mean, can you measure, you had some measurements out to 14 kpc, but I didn't see I don't know whether you were able to measure star formation out there, say with the H alpha or something.
You mean for the A-type stars plots I was providing?
Okay, yeah,
yes,
probably show them for the A stars, but then
yeah,
I'm thinking about
for the A stars, we can reach the outer part of the galaxies, but out there I doubt we'll find too many O stars already. So we do have a selection of all the northern galactic plane of O stars for width, actually, but we still have to look a bit more in detail about their distribution. But obviously, down here in the outer galactic plane, you'll keep finding less and less O stuff. But yeah, there are some studies from Maritza Pillani that do study this kind of stuff here. Maybe not too far away, not at 14 kiloparsecs. There won't be too many O stars down there, but maybe in this direction. Yeah, they do.
Yeah, there's some very weird chemistry going on out there, so I was just curious about whether you could see any stuff.
Well, I actually didn't mention it because I didn't have time, but one of the surveys in SCIP that we have is this high resolution survey in the anti-center. And one of the goals there is to compute some kind of metallicity in the anti-center direction. And we do expect to be reaching a bit far away with A stars in there.
Thank you.
We have to wait.
Great. I just wanted to remind everyone that since it's already late in Spain, Maria has agreed to be available to meet one-on-one if people have further questions or discussion on Monday, Tuesday afternoons. I'll drop the link into the chat again if you want to sign up to do that. I think with that, let's thank Maria again for a really interesting talk. And thanks everyone else for joining us. Great.
Thank you
Thank
very
you,
much.
Maria. That was great.
Thank you.
Bye.
Thank you.
It's been a pleasure.
Thank you.